The final whistle blows at a major sporting event. At that exact moment, 80,000 people stand up in unison. They all have the exact same thought: time to leave. 80,000 people is the population of a small city. Imagine placing an entire small city inside a commercial building and then asking everyone to walk out the front doors at the exact same time. If you tried to force that volume of bodies through standard building exits, the structural bottlenecks would fail almost instantly. Pressure would build, human movement would grind to a halt, and a fatal crowd crush would begin. Yet modern megastadiums routinely drain completely empty in under 20 minutes. The process is so smooth you barely notice it happening, and you certainly never feel like you are in danger. Emptying a building of this scale comes down to one mathematical constraint: throughput. You have a massive volume of human mass, but limited exit capacity. This animated diagram demonstrates fluid dynamics. When water flows from a wide reservoir into a narrow pipe, pressure builds intensely at the choke point. In a dense crowd, human beings behave almost exactly like fluid. Apply that exact physical law to 80,000 people trying to rush down the seating aisles to leave. The sheer weight and momentum of that human fluid hitting a narrow exit creates deadly pressure. Engineers solve this by avoiding a single giant ramp to the street. Instead, they build a cascading system of expansion zones, friction points, and precisely measured funnels designed to break the crowd apart before it ever reaches the outside world. To facilitate a safe exit, the stadium architecture must treat you, the sports fan, as a single molecule of water. The entire building is designed to manipulate exactly how fast and in what direction you flow. The control system begins the second you leave your seat. The first major choke point you hit is the tunnel connecting the seating bowl to the interior concourse. In stadium architecture, these tunnels carry an ancient name: the vomitory. This flow rate diagram illustrates the strict mathematics behind these spaces. The tunnels are not randomly placed. They are spaced to serve a specific maximum number of seats. The width of the concrete dictates a limit on how many people can pass through per minute. If a vomitory is built too wide, too much human fluid escapes at once. This floods the inner concourse with more volume than the next stage of the building can safely process. Conversely, if the tunnel is calculated too narrow, the flow of the crowd backs up into the seating aisles, creating frustration and the potential for a dangerous crush in the stands. This is the vomitory's true function. It acts as a nozzle. It restricts the initial surge of the crowd so that the subsequent architectural spaces can safely absorb the volume. Once you pass through that nozzle, the concourse completely changes its function. Hours before the game, it was an empty hallway for finding food. Now it acts as a massive expansion chamber. Because the concourse provides space for the restricted crowd to spread out, a new hazard emerges: velocity. If everyone in that wide concourse speed-walked directly to the nearest stairwell, a bottleneck would form at the top of the steps immediately. Since stadium designers cannot put up stop signs, they introduce invisible friction. They build the environment to actively slow you down without you noticing. Notice how heavily stadiums favor long, winding ramps over quick flights of stairs. A ramp physically forces the crowd to take a longer, slower, and much more measured path down to the ground floor, dialing back their walking speed. You will also find massive support columns strategically left exposed right in the middle of wide walkways. These act like rocks in a river, naturally splitting the rushing flow of people into smaller, slower, and more manageable streams. By the time you finally step onto the ground floor, the building has managed and diluted both the density and the speed of the human fluid entirely without your awareness. At the ground floor, the internal dynamics of the stadium crowd are fully stabilized, but the system's job is still not over. The crowd now faces the exterior gates and a final threat. If 80,000 people walk out of those doors and immediately step onto a standard 20-foot wide city sidewalk, the internal stadium system breaks down. The surrounding city infrastructure simply cannot absorb that volume of people at once. This causes a backup, pushing the crowd back inside. This is why modern stadiums sit inside a massive empty concrete perimeter. This outer ring, known as the plaza, is the system's final expansion zone. The plaza offers immense physical space. It forces the crowd to drop their speed to a normal walking pace, giving people room to check their phones and naturally drift apart. Color-coded signage then takes over to systematically fracture the crowd. The singular mass is sorted into tiny fractions, directed down separate paths toward distinct parking zones, highway ramps, and mass transit hubs. Leaving a stadium feels simple because the building has already done the heavy lifting. By managing pressure and creating invisible friction, the architecture treats the crowd like a fluid, safely processing the movement of 80,000 people and emptying the building, row by row.